So let's understand now the key features of the FEBIT algorithm. And let's start talking about the layer by layer approach that we use, which is the same as the one that a standard 3D printer employs. So we have our object, which is three-dimensional, and we slice it. And what we want is our algorithm needs to calculate what is the dwell time for each point that makes it possible that we have a constant layer height for each of the layers. If there was no interaction in between points, this would be relatively simple, but this is not the case because when I am depositing in a given point, I'm also affecting neighboring points. So this proximity effect is similar to the one that takes place in electron beam lithography, but here, of course, we are doing it in a 3D geometry, and this is FEBIT, this is not electron beam lithography. So the effect of neighboring points on a given spot can be mathematically written this way, where we will have that the layer height is equal to the heights of all the points that need to be taken into account, not only the point in which I am dwelling, but also all the neighboring points that may be also playing a role. And this is, of course, something that is this set of equations are very complex, because at the end, what I want to do is I want to extract the time. This is the key aspect. As soon as I know how much time I need to be dwelling on each point, I have solved the 3D printing problem. But this is not easy because of these couple equations that we have here. So we need to find an alternative way or a simplification of the process that allows us to get this time in general. For this, we have used the FEBIT continuum model that I introduced in a previous video, and we use the Langmuir monolayer adsorption, which is very typical in FEBIT. So the FEBIT continuum model is giving me what is the time evolution of the fractional molecule coverage. So how many molecules I have at a given time divided by the number of available sites, how this evolves as a function of time. And you can see that this time evolution depends on many factors. It will depend on how much gas is arriving and how many sites I have available. It will also depend on how much thermal desorption I have in an exponential way with the temperature. The higher the temperature, the more desorption I will have and less molecules on the substrate. It will also depend on how much electron dissociation I have. And then it also depends on how much diffusion, how much gas is coming through diffusion. And in this case, the f3ast algorithm is not taking into account the gas diffusion because this complicates significantly the solution of this equation. And we have seen that in many occasions, fortunately, this is not necessary, so we can get an analytical solution which simplifies the complexity of the algorithm. So the FEBIT continuum model can be expressed then as a function of these FEBIT characteristic frequencies, the one devoted to gas arrival, the one to thermal desorption, and the one to electron dissociation. And we can write in a more compact way this FEBIT continuum model. Once more, you can see how many parameters are in principle necessary in order to fully describe the FEBIT process, because it's very complex, but you will see that we have been able to effectively model this and simplify it significantly. So this is the equation where we have the parameters, the arrival of flux, the desorption, and the electron dissociation. And in principle, if we solve what is the height over time, taking into account this equation, it will be equal to this very complex equation where we see that we have a time evolution in these two factors with all the characteristic FEBIT frequencies playing a role in different parts of the solution. However, it is important to remark that when we have either very fast gas dynamics or long enough dwell times, which is typically the case because we are dwelling for milliseconds, whereas the gas dynamics take place more on the microsecond regime, the solution can be expressed as two functions. One that depends on the coordinates of the space. R is the distance with respect to the central point where the beam is scanned, so it's the radius, and directly proportional to the time. You can see that this is the final solution that is dependent on all these frequencies. But we are gonna basically centralize all of them into what I said, a function that we call S of R that depends on the coordinates of the space in a radial way and the time. So the height will be directly proportional to the time that the beam is being dwelled. So coming back to the set of equations that describe the height of one layer for consistent growth, you remember that in general it's a very complex computational problem, but if we make these assumptions that I explained before, the height can be separated in variables, and as a consequence, this expression can be expressed, this equation can be expressed simply like this, where the height of a given layer will be equal to the sum of all the points that I have been dwelling times this intra-layer proximity matrix, which is a symmetric matrix accounting for proximity effects of points within the same layer. And very importantly, because we have this separation of variables, the dwell times for each point can be directly calculated by solving this linear equation. And because we have this linear relationship, we can directly invert the matrix and obtain the dwell times, which is exactly what we need for 3D printing. So by basically assuming a stationary state, we see that we can separate these variables, of course not taking into account diffusion either. And that way we can obtain the dwell time. So this is great. The only important thing that we are missing in order to be able to 3D print is how to obtain this function f of S of R, which is necessary for the growth.